and good afternoon. I guess some of you just showed up in the room to have a good nap after this good lunch. And maybe some other came to hopefully listen to concurrent and asynchronous programming, which is a good thing because this is what I plan to talk to you about in the next 50 minutes. All right, so this talk is called Concurrent and Asynchronous Programming. It could also be called Concurrent and the End of Asynchronous Programming, thanks to Project Loom, because it's really what it is about, actually. The Loom project is an optimization in concurrent programming that will make the patterns that we've all been using for the past 10 years a little obsolete when you're using virtual threads. My name is José. I work at Oracle in the Java platform group as a Java developer advocate. And here are, oh, you can't see the slides. You know what? Oh, okay, thank you. That's better, I guess. Maybe one day we'll do slides-less presentations, but not today. So my name is José, and here are a set of links with content I like to publish here and there on the internet. If you check my GitHub account especially, you'll find a lot of content, a lot of demos, hands-on labs and this kind of thing about Loom, virtual threads, and structured concurrency. So you can definitely check that. We also have a website at the Java platform group that is handled by the DevRails, which is called dev.java. And it will soon be updated because we are just a few months away from Java 21. As you may know. And because Java 21 will get support from different companies, like LTS support, odds are that this is probably the next version that you'll be using, hopefully. Maybe some of you are already using Java 17? Yeah? Well, that's a good 30%, 40%, I would say. Java 11? Yeah, that's another half. Java 8? Oh, come on. Earlier than Java 8? Now you need to do something. You know that Java 8 has been released like 10 years ago, right? That's a 10-year-old version. Shouldn't be using that anymore. But you're missing so many new features and performances, by the way. Okay, and if you don't like websites, we also have YouTube channels. I'm the proud bartender of the Jeb Cafe, that you may already know. It's a YouTube series. And my friend Billy is doing the Inside Java, my friend Nikolai is doing the Inside Java newscast, and Billy is doing the sip of Java. The biggest difference between the sip of Java and the Jeb Cafe is that in the Jeb Cafe there is actually coffee in a cup, which is not the case for the sip of Java. And I would like also to talk to you just a few seconds about the Inside Java podcast, which is a great podcast if you like to just listen to interviews and this kind of thing. And we had very interesting episodes on the Loom project, which is what I'm going to talk to you about today. Especially the last episode, well, it's not the last one, but the Eliden and Nima and virtual threads by Thomas Langer is super interesting because he explains how he moved the Eliden web server to support virtual threads and the performance gains he got by using that. Okay. Before we start, just a word of warning, because Loom is still a work in progress, and I would like to say less and less a work in progress. It's not like people are stopping, you're working on Loom, but in the next version for Java 21, virtual thread, you see, there's nothing here near virtual threads. Where's my pointer? Okay, I can't find it. Should be somewhere. You see here, it's not written preview anymore. So that's a final feature of the JDK 21. Virtual threads are a reality. We'll have them, and so all the frameworks will be able to support them when the JDK 21 is released. And by the way, the release is in September, so it's really around the corner. So virtual threads have been integrated. Just to give you a hint on the amount of work it represents, that's a tweet that my friend David Delabasset made several months ago. To give you the size of the pull request, yeah, that's 100,000 lines of code. You already merged pull requests, right? Maybe not that big, yes? Okay. Maybe you've heard about code reviews. Yeah? So there was a code review, actually, after the merge. Okay? And there is still time for structured concurrency and scope values. I did this screen capture this morning, literally, and you can see that the review is supposed to end the 6th of June. So it's not integrated yet, okay, because integrated are the targeted JEPs, so they should not be here, they should be under this line. And if we're fortunate enough, maybe it will be done today, and if it misses the date of today, then it will be for 22 and not for 21, because there's only 1 day left to be able to do that. Structured concurrency, I'll just give you a hint about what structured concurrency is. You can definitely read the JEP, because JEPs are really interesting documents. They are meant to be read by normal people, okay, like us. And same for scope values, and I'll talk to you about these at the end of this presentation. And if you want to get any more information, if you want to provide feedback, report bugs, ask for features, or just provide comments or whatever, your one-stop link is this one, jdkjava.net/Loom. All right. Even if Loom is not there yet, it's still, as of now, it's in the JDK 20, it's still a preview feature. Many frameworks and servers and everything are already adopting Loom virtual threads. At least you have basically all the frameworks you can think about on this page. Vertex, Quarkus, Spring Boot, Tomcat, Eliden, which one is it? Jetty, Eclipse Jetty, etc. So on day one, Loom will be supported by probably by the frameworks you're already using. And I'll show you that with Spring Boot, hopefully before the end of this presentation. Great. Before we start, I just would like to talk to you about a little about concurrent programming, because Java in 1995 was one of the only languages to have a concurrent programming model baked in the language. Okay. In 1995, we had a class, the thread class, which we still have, basically. A thread class is a thin wrapper on what we call a kernel thread, that is an operating system thread. And we had a model for the task you can submit to thread, which is the runnable interface. Now, runnable became a functional interface in Java 8, and now you can implement runnables with Lambda expression. At the time, it was not the case. And if you want to synchronize stuff, you want to prevent a block of code to be executed by more than one thread at the same time, you have this synchronize keyword, which is a keyword of the language. And then in 2004, there was a first major update of the concurrent programming model with the first pattern that has been added, which is the executor service pattern. Now you're not supposed to handle threads by hand anymore. All you can do is just submit a task to an executor service. And by the way, a task can also be a callable, not only a runnable. And what you get in return is a future object. And you can interact with your task. You can even interrupt it if you want through this future object. And if your task is producing a result, because a callable can return something, it's not the case for a runnable, you can get to this result or this exception through this future object. And instead of using the synchronize keyword, you can also use a bunch of concurrent and synchronization primitives, like countdown latches, locks, semaphores, cyclic barriers, and the like. All right? And then in 2014, third update of the concurrent programming model. First, there is this fork join framework that is coming. Okay, so fork join framework is also a pool of threads. Now, it works in a different way than the executor service. The executor service, you have threads in it, and there is only one waitlist for your task. So you submit a task. This task is registered in a waitlist, and when the thread becomes available, it will take this task from this waitlist and execute it. Okay? In a fork join framework, the biggest difference is that you have one waitlist per thread. So if you have 8 threads, you will have 8 waitlists. And so it has been done like that because of parallel streams. In parallel streams, a given task can actually create more tasks. And these other tasks are going to be stored in the waitlist of the thread that actually created them. through the execution of this task, the first task. And it also implements another pattern called the work stealing pattern. So if there are threads that are not used, not doing anything, with empty waitlists, they will be able to go and visit other waitlists to steal tasks from this other waitlist. I'm telling that to you because it is actually used with virtual threads, as we are going to see in a minute. And of course, we have this wonderful framework called Completable Future. 10 years ago, Java embraced asynchronous callback-based programming model. It was in a mood 10 years ago. Everybody was doing that, RX, Reactor, in all kinds of languages. And Java did that too, okay? Everybody heard about callback hell? Yeah, right? Okay. If you didn't, just check on your phone what it is with your favorite search engine. Completable Future is the gate to the callback hell, actually. All these are the framework. So you can see that every 10 years, something is happening on the concurrent space in Java. Okay? You have a pattern here. And guess what? This is 2023, and Loom is coming. So the Loom train is on time, actually. Okay? But over all these years, there is one thing that was never changed in this evolution of the concurrent programming model in Java, is that once you have submitted a task to a thread, there is no way you can detach this task from this thread. So if for some reason this task is doing nothing, like not using your CPU, well, you just need to wait until this task will actually produce a result, so do something probably, or through an exception, or is interrupted through your future object. But the thread scheduler cannot say, okay, this task is not doing anything, I'm going to remove it from the thread and do something else with this thread. It's just not possible. And this is precisely what Loom is doing, so this is why I'm telling that to you. And by the way, I should think about moving the slides. Okay, so 2023, 2024, the Loom project, that has been, people have been working on that for more than 5 years now. It's really a huge engineering and research and development effort. Is there now because we have it in 21. What is Loom about? Well, that's quite interesting because you need to ask yourself, actually, why are you doing concurrent programming? Concurrent programming is hard to do, it's hard to write, hard to debug. If you see that you have a race condition somewhere in your application in production, we all know that fixing this kind of stuff is actually super hard. Okay? And there are two contexts in which you're using concurrent programming. And the first context is to speed up your in-memory computations, like parallel streams. You have a big array, like millions of elements in it, and you want to speed up this computation. Well, parallel stream will transparently and with quite an elegant programming model allow you to actually distribute this computation among all the cores of your CPU. If you have 16 cores, then all the cores of your CPU are going to be used just by calling parallel on the request on the web, an HTTP request, for instance, and you wait for the result. And you're not using the CPU. But the thread is still there, okay? You still need to pay for the cost a thread has. You're still using it, and this thread cannot do anything else, okay? So if you want to solve this, you have actually two solutions. Either you add more threads, or you change your programming model to be non-blocking. And this is what we have been doing for the past 10 years, okay? So the first thing you need to understand is that Loom is targeted as the second use case, increasing the throughput. Do not use Loom for your in-memory computations because it will not give you anything. So using virtual thread to run a parallel stream, for instance, is useless. Don't do that. You will actually probably decrease your performances instead of increasing them. Loom is really for I/O, and as of now, a network I/O, more than disk I/O. Okay. Suppose you have this kind of code, synchronous, imperative pattern. Some people call it boring code. I call it easy to understand code. Okay, so the first line is just the marshalling of a JSON object, your preparation of your request. The second one is your request itself. You're calling a web server, a REST server, whatever, something on the network. And then you get a result in the JSON object, and you recreate your model object with this. How is it going to be executed? Well, the first line of code, that's in memory computation. Okay, you will execute this line of code in the order of the nanoseconds, because this is the speed of the current CPUs. Maybe 10, 100 nanoseconds, something like that. And then you launch your request on the net, and here you're in the order of the milliseconds, 10 or 100 milliseconds. Okay, that's 1 million times slower. And then you get the response, you unmarshal it, you recreate your contract object in this example, and that's in the order of the nanoseconds again. So how busy is your CPU? How busy is your thread in this model? Well, it's idled 99.9999, and that's actually the exact number, percent of the time. Basically, your CPU is doing nothing if you do that. And that's a problem because you spend a lot of money on a very expensive CPU. Of course, you want to use it to speed up your application, but this programming model is not the right one, and we all know that. All right. Actually, if you want to put this diagram at the right scale, okay, the green part, if you have 2,000 pixels in the width of the screen, which is most of the time the case, the green part should be 1,000th of a pixel, and the red part, 2,000 pixels. Okay, that's the right scale. So how can you keep your CPU busy? Well, the first naive answer would be, okay, I need more threads. How many more threads? Well, 1 million. Easy enough. Can you launch 1 million threads on a machine? I'm not so sure. Okay. A thread in Java is a wrapper on a kernel thread. A kernel thread takes about a millisecond to launch and consumes about 2 megabytes on the stack. So there are good reasons for that. You want a contiguous zone of the memory for some reason. So yes, the allocation is 2 megabytes upfront. So if you want to launch a million thread, it will take you 1,000 seconds, which is between 15 and 20 minutes. That's probably not really what you want. And it will consume 2 terabytes of memory, which is also a lot of memory. Actually, if you take a Linux machine, odds are that a regular machine, like 16 or 32 gigabytes, odds are that you'll be able to launch maybe 3,000, 4,000 threads, something like that. Certainly not a million. So it means that you still have a factor of 1 million to gain. If you can launch 1,000 threads and you need to gain a factor 1 million for this stuff, okay, because this is what you need, then there is still a factor of 1,000 to gain somewhere. And this is why people have been using this kind of code, okay? Because because you cannot have so many threads, you need to change your programming model. And instead of having some blocking code, you have some asynchronous code that is non-blocking. And now your threads are doing 1,000 times more things than in the previous example, and you are gaining this amount of stuff. And by the way, asynchronous code can also run with much less than 1,000 threads because it really brings you a lot of performances. Okay, so this is the completable future API, but actually, all the APIs that you've been using are working on with the same idea. Okay, instead of having one blocking task, you split your task into very small, and nobody's blocking, no task is blocking, and then you run them asynchronously. But it gives you code that is hard to read, hard to write, impossible to unit test for some reason, good reasons actually, super hard to debug step by step, and we all know that, and impossible to profile. Why? Because when you look at the code that is currently being executed, what you see is actually the stack trace, well, the call stack of your framework, but not the call stack of your application. So you cannot profile it neither. And Loom is actually an effort to revisit that, to bring a new model of threads, to have cheaper threads that are called, in a Loom vocabulary, virtual threads. And virtual threads are actually 1,000 times lighter than kernel threads. And this 1,000 times is not chosen randomly. It has to be like that. If it's only 100 times, then you're doomed because you will not gain this factor 1,000 that you need. Okay? You really need to be able to launch 1 million virtual threads to keep your CPU busy 100% of the time. And if you can only launch 500,000, then you will still need to rely on the non-blocking asynchronous programming. So the effort will not be enough. Okay? So a virtual thread in Loom consumes memory in the order of the kilobytes. You can launch it in the order of microseconds. Okay? You don't need to pull it. So creating a pool of virtual thread is just useless. Don't do that because it's cheap to create and you don't pool resources that are cheap to create. Okay? And that's it. And you know what? I'm going to show you how it's working because do you prefer to see code in the slides or in the IDE? IDE? Slides? Okay, and the rest is sleeping. That's fine. I would do the same, so it's okay. All right, so hopefully I have an IDE there that really doesn't like PowerPoint, but that's okay. Please do something. Can I go presentation mode, please? Yeah, that's right. Okay, so we are going to, that's the good old pattern to launch platform threads. New threads start and join, okay? You'll know that. By the way, Loom brings new factory methods on the thread class. And you see I have an off-platform thread, off-platform or off-virtual to create a virtual thread. So I'm going to do off-platform and pass unstarted and pass this task as an argument. This task is just a plain runnable, and you shouldn't be there. Okay, and if I run this code, you know what? I'm going to copy-paste it directly to create a virtual thread at the same time. Okay, so we're going to do the same with a virtual thread. And you see that it's super hard to do that, actually, because all you need to do is change this to a virtual, and that's it. Okay, and you see that the virtual thread is also a platform thread, because the virtual class is actually, the virtual thread class is actually extending the thread class. I can show it to you. There is a virtual thread class. Yeah, virtual thread class. That's you. Where are you? You're there. You see, this class is final. It extends both virtual threads. That itself extends thread. It's not a public class, so you cannot compile code against this class, which is great, which is exactly what you need. You don't want to, when you design this kind of API, if you hide the class, it means that you can change it, which is great. Okay. I'm going to go back here. Okay, go back here and run new. I'm using Java 20. I'm not using Java 21 because I don't have everything I need in Java 21 as of now, which is fine. And you see that. So this is the string for the platform thread, thread 22, and this is the string for virtual thread. Okay, and you see that this virtual thread is actually running on top of another thread, which is a thread taken from a fork join pool 1, okay, and called worker 1. So actually a virtual thread is something that is running on top of a platform thread, and this platform thread, you don't choose it, it's actually invisible for you. This platform thread is taken from a fork join pool. And we're going to see why it's like that in a minute. So if you want to move your application from platform thread to virtual threads, super easy. You just need to change the thread you're using because virtual threads are an extension of platform thread and they fully support whatever is supported by regular threads, including race conditions, deadlocks, and this kind of good stuff. All right. I'm going to show you another example. Okay. Now what I'm going to do, so this code is just creating one virtual thread, Okay, I'm mapping this index to thread of virtual unstarted. That's fine. And this is the runnable. And you see that if the index is 0, not 10, if the index is 0, I'm just printing the name of the thread. And in the meantime, I'm sleeping for 20 milliseconds. And I'm going to do this a third time, and a fourth time. So if I run this code, excuse me, could I see my code? Okay. If I run this code, you see that this virtual thread is just running on top of worker 1, which is, okay, expected. And I'm going to take 2 virtual threads and do the same. And now you see that something quite odd is happening. While it was blocking, when it returned from this blocking call, which is the thread.sleep for 20 milliseconds, okay, it did not come back on the same platform thread. It came back on worker 2, then worker 1 again, then worker 2. And if I run it again, it doesn't have to be the same. Okay, I'm going to take 10 of these. And you see that it's jumping from 1 to 7, it stays on 7 and jump to 8. It seems to be random. By the way, I told you that you could launch many of them. Let me try 10,000. If it crashes, then you will see it because the laptop will crash itself. But you see that launching 10 virtual thread, which is already much more than what you can do with the platform thread, there's no real problem. It's very easy to do. Okay, if I want to run 1 million, which is the goal, actually, it takes a little more time, but not that much more time, actually. So it's okay to do that. So what is happening in this sleep method that I have here? Okay, thread.sleep, we're going to visit that. Okay, you see that we have a first block of code that is executed if the current thread is a virtual thread, and the rest is executed if it's not a virtual thread. By the way, this code is for people doing JFR. I don't know if some of you are doing that, but this is JFR code. Okay, so the virtual thread, there is a sleep nano code. Do sleep nano. I'm still in the thread class. I'm calling now do sleep nanos twice, here for JFR and here without the events. Do sleep nano, it's a private method. I have a call to park nano. Let us follow that. And then at some point, a call to this yield continuation method here, which itself is calling this continuation.yield method there. And this continuation object is actually at the core of this virtual thread technology. Okay? It's not a public object. Its package is a JDK internal VM, which basically means don't touch that. Don't write code against this class, even if it's public. You can still do it, but okay, don't do it. All right, and it's calling this yield method. So what is this yield method doing? I'm going to show that to you. So I just created a simple continuation object here on wrapping a runnable. That's my runnable. And I'm calling yield on it. I need this scope object, which is a continuation scope. That's technical detail. I'm going to run that. And you see that, okay, so I have an illegal access error, which is fine. Which is fine because I'm not allowed to use this continuation object. So I need to copy this and to tell him, it's okay, I know what I'm doing. I'm doing a demo, so please let me do that. I'm not running in production, I promise. Apply, okay, run. And now it's okay. All right, so here I'm just printing before continuation. I'm calling this continuation.run method because this is how you run a continuation. And then there is this yield called here, and then it gives back to the calling code. It goes back to the calling code and calls after continuation.run. Okay? But what happens if I do some call after that? Run again. Okay? And I'm going to after continuation.run, and I'm going to call run again, there, and then after continuation.run again. All right, so here I'm calling run twice, and there is a yield called in the middle of the runnable of this continuation. So let me run this code again. And you can see something very strange that happened. The first message is before continuation, then continuation.run, then yield was called, and the yield called actually gave the hand back to the calling code, right? To after continuation.run. It's like you have a return in the middle of a method, but with some code still after that you haven't executed yet. And if I call run again, then it displayed continuation run again, which is this message. So calling run, execute the runnable. Calling yield suspends the execution of this runnable. But if you call run again, the execution of this runnable will carry on where it was after the call to yield. Okay? And this is new. This is something that didn't exist before in Java. So wherever you are actually calling some code that is blocking, it could be in Java NIO, so all network code, everything, sleep, of course, synchronization, absolutely everything. Everything has been refactored, remember, 100,000 lines, all right, has been refactored to support this continuation object and to say, okay, if I'm blocking, I'm calling continuation.yield. And continuation.yield really means I do not need the CPU as of now because I'm blocked, all right? And if you're doing some I/O, for instance, if you're waiting for some data from the network, when the data is there, there is a signal at the OS operating system level, and this operating system level will trigger a handler, and this handler will call in turn continuation.run. So it will tell, hey, this code is actually needing the CPU now because the data is there, so you should be trying to run it. All right? What it's doing really is the following. I'm going to show you that on the slide because it will be easier to understand, I suspect. Okay, you have the heap memory, you have the platform thread for the fork join pool, and when there's a call to start, which starts your virtual thread, actually this virtual thread is mounted on top of a platform thread. Okay? If at some point this virtual thread calls is blocked, so calls continuation.yield, at this point, the stack of this virtual thread will be copied from the stack of this platform thread to the heap memory. Okay? You see, that's exactly that. It's copied from the stack to the heap memory. And beware, because at some point it will have to go back. And we didn't even rehearse. Okay? And when you're calling continuation.run, then this portion of stack you have in the heap memory will be brought back in this fork join pool. Now, it will not be brought back directly on the thread that executed it in the first place. It will be sent back, well, there's a handler involved, etc., but whatever. It will be sent back to the wait list of this platform thread. And remember that it's a fork join pool. If this wait list is full and if this platform thread is busy doing something else, then another platform thread can actually steal this task. And this is what we're observing when we see that this virtual thread is jumping from one platform thread to the other. Okay? So this is how virtual threads are working. This is how threads are working. For the first time, when a task is blocking, it is now possible to take it away from the platform thread that is actually executing it, okay, and bring it back when it's free to run again. And this is completely new in Java. This is completely new in Java. Okay, how many platform threads do you need to run 1 million virtual threads? I have another piece of code for that. So there is a wonderful regular expression there. Everybody loves regular expression? Yes, I do. Okay, so we are going to launch 1 million thread again. We are just going to block for 1 millisecond. You know what? We are not going to block because we don't need it. Okay, So I'm going to comment this code. Oops. Okay. Great. So I'm just going to run this, and it will analyze the name of the virtual thread to extract the worker that is actually running it, add everything in these two concurrent sets. Concurrent hashmap, new key set is just a set, actually. Okay, and we are just going to measure the time it takes to run all this. So, yeah, let me run this code. It will also display the number of cores I have on this laptop. And you see that the result, I mean, launching and running a million virtual threads, it only took less than a second, right? So it's really, creating a virtual thread is really in the order of the microseconds. If it was not, there was no way this code would have been executed as fast. So the fork join pod that is running the virtual thread has 11 platform threads, and these 11 platform threads are enough to run this million virtual threads. So actually, you don't need that many platform threads to run this kind of patterns of code. All right, here are the worker thread that you used. And if you are on a 16 cores machine, then you will have 16 platform threads to run your virtual threads. So that's it. That's the gist. Now we have virtual threads that are super cheap to create, super cheap to block, because the cost of blocking a virtual thread is just the cost of moving the memory from the heap to from the stack to the heap, back and forth. So much less expensive than blocking a platform thread, and we can use them to create new ways of application. There is still a little problem that I'm going to show you real quick with synchronization. Because maybe some of you wrote some C or C++ code in the past, and you know that in C or C++, you can actually get addresses on the stack. Okay? In a C function, if you have a variable, int I, that has been declared, then you can get the address of this local variable, and that's an address of the stack. So if you want to move the stack from one place of the memory to the other, namely from the stack of the platform thread to the heap, and there are addresses on the stack in this piece of code, then you may be in trouble, because when you are going to take this back, odds are that the addresses are not going to be the right one anymore. Okay? So every time there is a native call, basically, in a stack of your Java application, then the following is going to happen. I'm going to show you. This is basically the same code as previously. I'm just running 100 virtual threads, and I'm just doing some synchronization in the middle. There is no sleep whatsoever. I don't need that. And what you see is not very nice. Okay? What you see is that the virtual threads I have are not jumping from one platform thread to the other anymore. And the reason is that if you have some native code in the execution of your thread, then your virtual thread is said to be pinned on the platform threads, because it would be dangerous to move it, because in this native code you could get some local addresses on the stack, and you don't want to corrupt them. It would corrupt them if you do that. All right? And in this synchronized keyword, there's no native code per se, but there is an array, and the address of this array is an address on the stack. So the way synchronized blocks are working are currently being worked on to refactor that and to remove this native array. So if you have a synchronized block in your task, then the virtual thread will be pinned to the platform thread, and basically you lose all the gains you could get from moving this virtual thread to the heap. So it's probably bad. What should you be doing if you are in this situation? Well, you should be doing, the first thing you should be doing is see if your application is actually having performance issues. And if it's not, do nothing, because you don't fix something that is working. Okay? And if it has some performance issues, check what is happening within your synchronized block. All right? If you're just having a synchronized block that is there to guard some kind of concurrently accessed variable or structure, some kind of in-memory computation, then it's not too bad. Odds are that you will not observe any kind of performance loss. All right, so don't do anything. If you have some I/O stuff that is going to block your thread for several milliseconds, then all you need to do probably is to replace that with a good old reentrant lock. Okay, that's the exact same code with reentrant locks. And if you run that with reentrant locks, then you don't have this problem anymore. Your virtual threads are not pinned on the platform threads again anymore, and then the problem is fixed. But once again, make sure that you have real performance issues before trying to refactor your code, because odds are that you will not have issues. Okay. I would like to show you how Spring is working with virtual threads. Okay, so I have a Spring app class here with this protocol handler virtual thread executor customizer. The bean that is written by this method, well, it's technically not a bean, but whatever, is actually the executor service that Spring is going to use to handle all your synchronous calls. All right? So far, this bean is commented. So I'm just going to run this Spring app. Could you run this for me, please? Thank you. And I would like to show you two things. Yeah. Localhost. Okay. So the first thing I would like to show you is the current thread. It's just a service that displays the current thread, and you can see that it's a regular platform thread, okay, which is expected. And if I run this code, which basically just throws an exception, that's the stack trace that Spring Boot is generating. So I have a null pointer exception there. Okay, and if you check all the stack trace, you see that it starts at thread.run, which is the platform thread. Now if I stop this, uncomment this bean, so this factory method from the executors class is actually creating an executor service that is basically empty. There's no thread in it. And every time you submit a task to this executor service, it will create a virtual thread for you on the fly and let it die. It does not pull it, because you don't need that. So let me run this code again. Okay. And let me check this current thread. You see that the current thread is now a virtual thread, and if I refresh, you see that it's always a new virtual thread. The counter keeps incrementing itself. It's not taken in a pool, because there's no pool, basically. And if I throw this exception, I have the exact same stack trace. That's my code, the 2 lines. Then that's the Spring Boot code. And you will see that at the very bottom of it, let me zoom this. Okay, you see that you are actually in a continuation.enter. So it's not run, it's enter, but doesn't matter. Okay, and in a virtual thread. The continuation is actually running this virtual thread. Okay, underneath there is actually this handler. And this handler we call continuation.yield and run to yield the continuation and run it again when your code is blocking. So actually, the Spring Boot is ready, and it has been ready since last November, I think, to support virtual threads. So you'll be able to use them as soon as everything is published. All right, we just have several minutes left. So let me just, I'm going to leave this presentation mode because that's going to be better, and go back to the slides. I just would like to show you the kind of patterns that, now that you have all these threads, the idea is, okay, do you really want to continue writing this kind of code at the bottom? The goal is really to get rid of this kind of code. So I'm just going to show you an example, which is you build a travel page, and there are 2 informations on this travel page. The first one is a quotation information, so the price of the travel, that is obtained by querying some REST service somewhere on the internet. And the second one is the weather forecast. You want to make sure that your people are going to buy your travels. So you want to tell them, hey, yes, the sun is shining there, you should definitely go there. And if you want to implement this simple, I would say, toy example, the completable future pattern is this one. I wouldn't say it's impossible to write. I wrote it, so it's almost okay. But you'll probably take a few minutes to really understand how this code is working, right? It's not super easy to understand how this code is working. And actually, the real problem you want to solve is not this one, but it's this one. Okay? You want to query several quotation servers and get the best one. Okay, so there's a mean to be computed there. That's some kind of business rule. And you want to query the weather forecast, but the weather forecast, you want to get the first one, the first weather forecast server that is going to answer. So that's a different business rule with time involved. The patterns brought to you by structured concurrency are these ones. You just create an object called weather scope, and we're going to take a look at this object in a minute. And this scope object, it looks like an executor service. You submit tasks to it with the fork method, fork, fork, fork. Every time you want to submit an asynchronous task to it, you just call fork. And when it's done, you call join, and join is a blocking code. But because you're blocking a virtual thread, it's okay. It's okay to write blocking code. When join is done, then you're sure that all the tasks that you launched either have produced a result or through an exception. Okay? So you can just add a get first weather on this weather scope to get the first weather that has answered. And for the quotation, it's exactly the same. Okay? You submit your requests, HTTP request on your quotation REST server. You get the best quotation, and that's it. And to build the travel page you want, well, it's the same. You call get first weather, so that's a third scope. Guess best quotation, you just combine the different elements you need to build your travel page, you return it, and that's it. So the pattern is always the same. You fork your task, call join, get the results, all the exceptions, and that's it. And all the code you need to write in the quotation scope, for instance, is this one. It's a callback on the completion of your task. As of now, it takes a future object. That may change in the next version of the structured concurrency API. Basically, you have 4 states: running, success, fail, and canceled, and that's it. If you get a result, you put it in a collection. If you get an exception, you put it in another collection, and that's it. And once you're done, so when the join has been called, well, all you need to do is to analyze the content of this stuff, and that's it. All this code, okay, this code and this one, this is imperative, mono-threaded blocking code, which is fine. By the way, this code is not blocking, but this one is blocking. But that is fine, so it's much easier to unit test. If you want to execute it step by step in the debugger, it's super easy. And if you want to profile it, you can also do that. And it will profile your application and not the framework, basically because there's no framework. Okay. Well, I think I have 1 minute left. So that's it for today. Loom is great. And the good news is that it's here. Thank you for your attention. I think we have some time for questions. Is it okay if you take some questions? Okay. So if you have questions, we have some time for questions. Yeah, there's a question here. Yes, it's working.
How would you compare virtual threads to coroutines or pattern?
They are not the same. It's not coroutines are not built on top of virtual threads because coroutine doesn't have virtual threads yet. So actually it would be more interesting to compare that once virtual threads are actually a final feature of the JDK and once Kotlin updated itself to virtual threads. But currently, coroutines are built on top of platform threads, so you get the performances of platform threads with them.
So you're saying that coroutines could make use of virtual threads?
You need to ask this question to the Kotlin guys. But I suspect that they are fully aware of what virtual threads are, and they are probably working on leveraging this feature. Well, but it's really a question for them. Welcome. There's another question. Maybe you can shout your question, and I do my best to hear it. Hello. So ThreadLocal variables are fully working with virtual threads. So everything you can do wrong with ThreadLocals, you can do as wrong with virtual threads, which is great. That's super good news. Awesome. But there's another model that I didn't, I just very briefly mentioned it at the very beginning of the presentation, which is called ScopedValues. So ScopedValues is another model for ThreadLocals that is also coming. And that will be a much better, is meant to be a replacement for ThreadLocal variables, and that will fix many of the problems of ThreadLocal variables. No, there are many issues with ThreadLocal variables. I'm not going. Yeah, there are many issues. But if you have an application that is working with ThreadLocal variables and you don't just want to move it to virtual threads, it will work out of the box because it's fully supported. So you will be able to, to use them.
So you showed us the code for the thread sleep method.
Yeah.
And I noticed that basically you guys added a check to see if the thread was a virtual thread in that case. How will that affect anyone using the further Java versions with simple threads, always making that check?
You mean if you're using Java 17, for instance?
No, the future version that will include the project Loom, because of the thread.sleep, you'll be always checking if it's a virtual thread.
Yeah. Every time you call thread.sleep, as of the JDK 21, it will check if the thread is a virtual thread or not. And if it's a virtual thread, it will call continuation.yield. So your virtual thread will be moved from the stack to the heap and will be moved back when your counter is done after the number of milliseconds you decided to pause your thread. This is how it's going to work. But it's only work for virtual threads. It's not working for platform threads. Is it your question?
Yeah, I was just wondering why that decision instead of splitting.
Oh, because platform thread, kernel threads are not, there's no continuation within a kernel thread. Okay, the continuation is actually executing your virtual thread. This is what I showed you on the Spring Boot stack trace. You have continuation that it was enter, not run, and then you have the virtual thread on top of it. Okay, but the kernel thread, there's no continuation underneath, so you cannot do that. You cannot call continuation.yield because you're not actually executed by a continuation object.
Okay. Thank you.
Welcome. Hello?
One question regarding the stack and the heap.
Mm-hmm.
So, is there any limitation of memory when we pass from the stack to heap? Because if we have, 1 million virtual threads and we are stacking them in the heap, how do we avoid a stack overflow?
A heap overflow, you mean? An out-of-memory error. Well, if you are hitting this limit, it means that in the first place you couldn't allocate all the memory. Right, so you are basically not running in a memory space that is large enough. But a virtual thread, even if a virtual thread takes 100 kilobytes, if you multiply that by a million, how much is it? 100 gigabytes, is it? But it's not 100 gigabytes because I have 32 gigabytes on this laptop and I could run a million virtual threads with no problem. So, yeah. But it just works. You don't need that much memory to do that. So it's okay. Running a million virtual threads in a virtual machine running on a machine that has 32 gigabytes is okay. And It doesn't even slow the machine. So that's not an issue. That's all I can say.
Makes sense. Yeah, sorry. Thanks.
This one is simple. What is next?
You mean in Loom?
Yeah.
So there are several next steps. One of them is to optimize the synchronized stuff that I showed you. And that is not, that is a little annoying currently because you have this spinning issue that people would like to get rid of. There are also some optimizations that are currently underway to diminish the amount of memory that virtual threads are consuming. And there are several optimizations that people have in mind that are going to be done at the JVM level, in the garbage collectors and stuff, to do that. The structured concurrency API is still a preview feature, so it needs to be finalized, made final at least, and published in a JDK, and the same for ScopedValues. So there's still work underneath, and once everything has been published, virtual threads almost done, will be done in a few months. Structured concurrency, still preview. ScopedValues, still preview. So when everything is done, there are probably more optimization that people will add to the JVM to run the virtual threads faster and with less memory. Yeah, so there's still work to be done. And after that, I don't know. Okay, thank you for your attention. Have a great rest of the day.